In this lecture, we'll be discussing about inverted page tables. So let us see what is this inverted page tables and why is it used. So in most operating systems, a separate page table is maintained for each processes. So we have seen so far when we were discussing about page tables and paging that in most of the operating system, there is a separate page table that is maintained for each of the processes. So for n number of processes, there will be n number of page tables. So if we are maintaining a page table for each process, so if we are having n number of processes, there will definitely be n number of page tables. So this is very evident. So for large processes, there would be many pages, and for maintaining information about these pages, there would be too many entries in their page tables, which itself would occupy a lot of the memory. So this is a problem here. When we are maintaining a page table for each processes, when we are having too many processes in our system, then there will be too many page tables that we have to maintain. And then depending upon the data that is present in each pages, the size of the page table itself will be too much, and it will be a task for maintaining these many entries in the page table, as this itself will occupy a lot of our memory. So this is a problem that we have. So hence memory utilization is not efficient, as a lot of memory is wasted in maintaining page tables itself. So let's say that we have a process and the process is divided into pages, and we have a page table that maintains the information of all these pages. Now, among these pages, some of the pages may be loaded onto memory and some may not be loaded onto the memory. Now, even though some of this process may not be loaded onto the main memory, still the page table has to maintain information about that page. So if we go on like this, as we said, a lot of memory is going to be wasted for maintaining the page tables itself. So what is the solution for this? So the solution to this is use inverted page tables. So we will see what do we mean by these inverted page tables and how they work and how they are able to solve this problem that we just discussed. So here, an inverted page table has one entry for each real page or frame of memory. So like I explained in the previous slide, the pages of the processes, though they are there in the page table, does not necessarily mean that those pages are loaded onto the memory. So in inverted page tables, what we are going to do is, instead of maintaining information of all these pages, we will be maintaining only one entry for each real page or frame of memory. That means if a particular page is there in the main memory, if it is present in a particular frame, so for that frame, we will be maintaining an entry in the page table. So this is the difference here. One entry for each real page or frame. So when I say real page, remember that this is a page that is present in the main memory. So that is why we are also using the term frame here, because we know that in main memory we have the frames. So for each of this real page or frame, only for that there will be an entry in the page table. So each entry consists of the virtual address of the page stored in that real memory location with information about the process that owns that page. So here, since our page table is going to be indexed with reference to the frame numbers, there is one more data that we need to maintain in that page table. And what is that? That is the information about the process that owns that page. So definitely the page number will be there, and along with the page number, we are also going to have the information about which process owns that particular page. So these are the two information that need to be there in the page table. So remember, in the page table, it will be indexed on the basis of frame numbers. And then inside the page table, we are going to have information about the process that owns the page and the page number itself. So thus, only one page table is in the system, and it has only one entry for each page of physical memory. So if we are following this, we need to maintain only one page table instead of having a page table each for all the processes. And in this one page table, it will have only one entry for each page of the physical memory. So if we are doing this, the size of our page table will be like the size of our main memory. So instead of having a very big page table or many page tables, we'll have one page table whose size will be almost equal to the size of our main memory, because we are storing the information about each real page or frame. So the maximum size that we can have for the page table will be the maximum size of our main memory. Hence, we are reducing the usage of memory that we use for storing page tables. So now I hope you got an idea of why we are calling it inverted page tables. Why? Because here we are indexing the page table with reference to the frame, and then inside the page table we are having information about the process and the page number. So it is opposite, because in the normal page tables that we have discussed, we are indexing the page table with respect to the page numbers, and inside the page table we are having the information about the virtual page number and the frames. So we see that how this thing has been inverted in this scenario. So that is why we call it an inverted page table. So when we are applying this inverted page tables, or when we are making use of this, the virtual address in the system will consist of a triple or three fields. And what are they? They will be process ID, page number, and offset. So in normal paging, we saw that the virtual address has only two fields, the page number and the offset. But here we also need to include the process ID here to identify to which process does this particular page belong, because we know that in our page tables we are indexing it in the inverted way. So because of that, we need information about process ID as well. And then each inverted page table is a pair of process ID and page number. So as I already said, inside an inverted page table, we'll be having two things, which is the process ID and the page number. Okay, so let us see the working of this now. So coming to the working, the first step is when a memory reference occurs, part of the virtual address consisting of process ID, page number is presented to the memory subsystem. So when we want to make a memory reference, the part of the virtual address. So why are we saying part of the virtual address? Because we saw that in virtual address there are three things: process ID, page number, and offset. So a part of it which consists of two things, which is process ID and page number. So these two things will be presented to the memory subsystem. And now what happens? The inverted page table is then searched for a match. So we will be looking up in the inverted page table if we have a match for this particular process ID and page number. So if a match is found, say at entry I, then the physical address I and offset is generated. So if we are having a match for this process ID and page number, and let's say that that match is found at entry I. So remember, in inverted page table, we are indexing it with reference to the frame number. So entry I would mean the index I, which is the frame number. So if we are finding a match, means entry I is the frame number that we want. So the physical address is generated by combining this frame number, which is I, and the offset. So offset is a part of the virtual address which will also be present there. So these two will be combined, and hence the physical address will be generated. If no match is found, then an illegal address access has been attempted. So once we look up, and if we are not finding a match, that means it is an illegal address access that has been attempted. Okay, so I hope you have an idea now about the working. Now let's take a diagram to visualize how this works to make it even clearer. So here is a diagram that shows an inverted page table and it's working. So here we have the CPU, then we have the logical address, and this is our page table and the main memory. Okay, so let's see how it works. So the CPU will generate the logical address. So here, remember, as I already said, the logical address will consist of 3 fields. What are they? Process ID, the virtual page number, and the offset. Now, a part of this logical address is passed on to the memory subsystem. That's what we saw in the working. So what is the part that is passed? We are passing the process ID and the page number to the memory subsystem, and it will come here and it will look up for this particular process ID and page number in our page table. And remember, this is the inverted page table. So in inverted page table, what do we have? We have entries consisting of PID, process ID, and page number, and they are indexed with respect to frame numbers which are present in the physical memory. So this I that is given here, it represents the frame numbers. So this page table is indexed with respect to the frame numbers. So we are going to search for this particular combination of process ID and page number in our page table. And let's say that we are getting a match here. So suppose this is a match, PID and P we found here. And let's say that it is present in the ith entry. So ith entry means it is the ith frame number. So that frame number will be passed on here, and combined with the offset from our logical address, which is D, the combination of this will form the physical address, which will give us the address of that particular page in our physical memory or main memory. So this is how an inverted page table works. So here, instead of having page tables for each of the processes, we will be maintaining one page table, and in that page table we'll be having information about the process ID and the page number, and they are indexed with respect to the frame numbers which are present in the physical memory. So I hope you understood why it is called inverted page table. I repeat again, because it is indexed with respect to the frame numbers. In the normal paging that we have discussed, the page tables are indexed with respect to the page numbers. So here it is the opposite. So this is how it works. Now let us see what are the advantages of this and if there are any disadvantages of this inverted page table. So coming to the advantages of inverted page table, the first and foremost advantage is it reduces memory usage. So this was the main reason we even came up with the idea of inverted page tables, because we wanted to reduce the usage of memory by not maintaining a separate page table each for all the processes, but by having just one page table. So definitely the memory usage is reduced, and hence we have an efficient usage of our memory. So this is the biggest advantage that we have. Now coming to the disadvantages, the disadvantage is increased search time, as inverted page table is sorted by physical address, but lookup occurs on virtual addresses. The whole table might need to be searched for a match. So here the lookup time or the search time is increased here. And why is that? That is because, as I already showed you, the page table is indexed on the basis of physical addresses or the frame numbers that we have seen. But when we are looking up for something, we are looking up on the basis of the process ID and page number, right? When we were searching it, what were we passing? The process ID and the page number. So it may not be in a sorted order. This process ID and page number combination in the page table may not be in a sorted order, and hence we may have to search the entire table in order to find a match. So because of that, there is an increased search time in this inverted page table. So this is one of the disadvantages of inverted page tables. And another disadvantage is difficulty in implementing shared memory. So in one of the previous lecture, we have discussed about shared pages, and we saw how different pages were sharing the same location in the physical memory frames. So with the concept of this inverted page tables, where we are maintaining one entry each for each real frames in main memory in the page table, it may be difficult to implement sharing. So shared memories implementation is going to be difficult in inverted page tables. So these are the two disadvantages that we have in inverted page tables. So the main reason why we wanted to have this is to reduce memory usage, and that we could do it. So I hope with this, the concept about inverted page tables and its working are clear to you. Thank you for watching, and see you in the next one.